The motto of today's webinar is to make all of you very, very comfortable with fundamental concepts of dynamic programming. Okay, but before I start doing that, I would like to hear it from you that how many of you here are totally new to dynamic programming? Just say yes, those of you who are new to dynamic programming. Maybe you have not done a lot of questions based on that and you would want me to start from the fundamental concepts of it. I see that there are some of you out there. Okay, cool. So the way I would be doing it, would be, I would start from the basic fundamental concepts and then we would touch upon some questions. And of course, I would start with the basic questions and touch upon some mediocre questions and try to do as much as we can cover in this time. Okay, cool. So let me ask you one simple question. Let's say I have an array of numbers. Let's say I have an array of numbers. Okay. Now, let's say the array of numbers contains few numbers like these: 1, 4, 10, 11, and then 2. Okay. Let's say these are the numbers. Okay. Now, let's say I somehow know the sum of numbers from here to here. Okay, and I would denote that as sum 3. So sum 3 means sum of all the numbers starting from index 0 and ending at index 3. So this would be equal to something, right? So in this case here it is 4 plus 1, 5, 15, and this is 26. So this thing is actually 26. Okay. Now let's say I want to find sum from here to here, which would be called as sum of 4. Okay, so sum of 4 says sum of the numbers from 0th index to 4th index. Okay, now if you have the answer of sum of 3, can you quickly tell me the value of sum of 4? Can I quickly comment on sum of 4 if I have pre-computed sum of 3, if I know that? The answer is yes. So essentially sum of 4 is nothing but sum of 3, which is sum from here to here plus the 4th number, okay, which is array of, that index would be 3. Okay, sorry, array of 4, which is this number. Okay, so the idea that I'm trying to build from here is that this is a small problem and this is a bigger problem. Okay, so what I mean by that is, if let's say I have solved a smaller problem. Now problems are small and big in terms of in terms of the size of input. So here the size of input is small and here the size of input is larger. So if I know the solution for a smaller problem, then I can easily comment upon the solution for a larger problem. Okay, so this, if you understand, this is the first symptom of DP. This is the first symptom of DP, wherein if I have solved smaller sub problems, then I can easily solve bigger problems. Okay. Also, now let us consider another scenario. If I had not remembered this sum of 3, okay, then in order to find the value of sum of 4, how much time would have been taken? How much time would have been taken? What would I have been required to do? I would have been required to make the sum from here to here again, right? So this is one basic thing that you all should understand, that if I have pre-computed something, if I have solved smaller problems, I can use those solutions to solve larger problem in just order one time, by just order one operation. But if that is not the case, I would end up requiring more time. Okay, cool. So this is first thing that you should understand. And now this particular thing where, solution to a bigger problem depends upon solution to smaller sub-problems. This particular thing, if you find in any problem, then you can very much say that, hey, this problem exhibits the symptoms of DP, so I can think in the direction of DP. Okay. So I think this was very simple to understand. How many of you understood it? Just say yes, those of you who understood it, what I tried to convey from here. Okay, if you have any doubt in the between, you can just ask me. Okay guys, so based on what we have just done, let's take example of another array. So let's say my array contains numbers like -1, 2, 0, 4, 3. Okay, let's say these are the elements of the array. Now what I want to do, I want to create another array called as max. I want to create another array called as max. And what I want, that max of I, which is ith element, that should contain the maximum of numbers from 0 till I. Okay, I want that. Okay, so is that clear what I tried to say? Max of I should contain the maximum of A0, A1, so on till A of I. Is that clear? Okay, so let's say if I have to do that, what should max of 0 contain? Max of 0 should contain the maximum value that I can get from 0 to 0. And that is just one value, which is -1. Can you tell me what should be the value of max of 1? What would be the value of max of 1? What is the maximum value from here to here? That is 2. Okay, what is the maximum value from here till here? What is that? That is also 2. What is the maximum value from here to here? That is 4. And what is the maximum value from here to here? That is also 4. Okay. Now guys, see, one most inefficient and brute force way to do that would be, whenever you have to calculate max of I, you can just run a loop from 0 to I and compute the maximum. Okay, but that is an inefficient way of doing that, because here one thing that I can see is that, let's think of it in this way, that if, let's say this is my array. Okay, now let's say I know the maximum value from here to here. That maximum value, let me call that x. If I know the maximum value from here to here, can you quickly comment on the maximum value from here to here, which is still here? Can you comment on that in order one time? The answer is yes. Let's say the maximum element from here to here, that was 9. Okay. And let's say this new element is 5. Okay. Then the answer is going to be 9, right? But had it been 15, the answer would have been 15. So the only two things that I would be interested in would be maximum in this part and the new number that I got. So can I write something like this, that maximum from 0 till I plus 1 is nothing but it is max of either max till I or the new number that I got. Is that clear? Is that clear? Just say yes, those of you who are clear with this, that how knowing the maximum value till smaller subarray can help me solve for the larger subarray. Okay, cool. So I believe this much should be clear to all. Now, this overall thing where a solution of a problem of size S depends upon solution of the same problem but of smaller size. This thing is called as optimal substructure. Optimal substructure. Okay, that my problem solution depends upon the solution to its various subproblems. Okay. Okay, guys. Now tell me, can you think of any very classical problems that all of you have done? Any popular sequence that exhibits this kind of characteristic, where let's say a larger value depends upon much smaller values? Yeah. So somebody is saying Fibonacci. Exactly. So what is the recurrence relation or formula that you have for Fibonacci? Can somebody tell me that? So very simple. That is actually f of n is equal to f of n minus 1 plus f of n minus 2. Right? This is the case. Okay. Now, also, is this formula true for all values of n? Is this formula true for all values of n? The answer is no. This is not true for all values of n. This is true for all values of n which are greater than or equal to 2. Okay. And for f of 1, this value is 1, and f of 0, this value is 0. Okay. So now, since all of you were there in recursion's webinar, and I hope you all are comfortable with recursion. So if, let's say, I go on and write recursive code for this, how is this going to look like? So let me just write a quick recursive code to find nth Fibonacci number. So if I do that, let's say I have a function int 5. It takes in an integer x. Okay. So basically, the responsibility of this function is that it is going to return me the xth Fibonacci number. Okay, I want xth Fibonacci number. So first of all, what should I write? I should write my termination conditions. So termination condition is that whenever the value of x is 1, I should return 1. If it is 0, I should return 0. So maybe I can code it like this, that if my x is smaller than 2, simply return x. Okay, if my x is smaller than 2, simply return x. Else, for all larger values of x which are greater than equal to 2, I need to call Fibonacci of x minus 1, and whatever is returned from here, I need to add that with Fibonacci of x minus 2. Okay. Now, see, here you can easily see that there is a larger problem dependent upon solutions to smaller problems, smaller subproblems. Now just tell me one thing, that is this efficient? What would be the time complexity? What according to you should be the time complexity of this? Okay, some of you are commenting 2 raised to power n. Okay, so let us see what is actually happening behind the scene when this code actually gets executed. Okay, so let's say I call this input for x equals to 5. Okay, I called this input for x equals to 5. So what happens is that first Fibonacci of 5 gets called. Okay, now which of the following instructions will get executed? This instruction will get executed. So what will happen is it will call f of 4, and it will also call f of 3. Of course, this will be executed once this has finished execution, and then whatever comes from here, it will just sum them up and then return it out. Okay, this f of 4 is going to return f of 3 and f of 2. Okay, and this f of 3 is going to call f of 2 and f of 1. This f of 1 is going to be a termination condition. Okay, I'll simply return 1 over here. This f of 2 is going to call f of 1 and f of 0. These will be termination conditions. Okay, can you see one thing over here, that essentially what is happening, that when I am here, I have done this much amount of work to figure out the value of third Fibonacci number, right? I'm going to figure out the value of third Fibonacci number. And when I am here, again, I would end up doing the same thing. I would have to do this amount of work here again. So what I mean by that is that this problem, this subproblem, let me call this subproblem, is repeating. this subproblem is getting repeated. How many of you can see that the subproblems here are getting repeated? Just say yes, those of you who are able to see that. Yeah. So if you can see that, this clearly is a very inefficient way of doing things. Okay. So now let's say I have to comment upon the time complexity of this. Okay. So so right now we will not make exact guess that exactly how many operations are going to happen. We'll make a very wild guess which will be somewhere close to the exact number of operations. Okay. Cool. So let's say you are finding nth Fibonacci number and then you are using this thing. So f of n calls f of n minus 1 and f of n minus 2. And then this again will call two things and so on and on. One thing to understand here is that it might happen that some of the paths might end earlier than the other paths. Okay, there can be some paths that end later than the other paths from root till the leaf. Now, can you tell me what would be the height of this tree? By height of the tree, what I mean is what would be the length of longest path from root to any leaf in terms of n? Can somebody tell me that? That would be n. The height of this tree would be n. And from which branch it would come out to be n, that also I can tell you. F of n calls f of n minus 1. F of n minus 1 calls f of n minus 2. This calls f of n minus 3. This goes on and on and on till it reaches f of 1. So this would definitely be of height equals to order of n. Is that clear? Is that clear that the longest path that one can ever create in this recursion tree would be of size n? Okay. Now, as I already said, that there would be some paths which will have a smaller length than this. But can I say on an average, here there will be one function call in the level 0. In level 1, there will be 2 function calls. In level 3, I have 4 function calls, and so on and on and on. Till level n, I'll have something like 2 raised to power n function calls. So if you sum over this GP, this comes out to be order of 2 raised to power n. So of course, total number of calls will definitely be lesser than this, but somewhere closer to this. Okay, so this is a very high complexity algorithm. Because if let's say you have to find n equals to 100 Fibonacci number, 2 raised to power 100 is a very, very big number. Okay, so is that clear? Now, how many of you are comfortable with the huge time complexity of this thing and why this is a really inefficient process? Okay, so tell me now, if I want to optimize it, how do I optimize it? How do I optimize this? So what is the most basic thing that comes to your mind for optimization? Okay, so think of it in this way. When I drew this, I solved for third Fibonacci number over here. Okay, and now I might again solve for third Fibonacci number over here. Okay, so how about doing something like this, that once you have solved for third Fibonacci number, store it somewhere in the memory, saying that, hey, third Fibonacci number is equal to some value alpha. Okay, and when the call for third Fibonacci comes again, then simply check whether I have stored its solution or not. If the solution is stored, just return the solution. Is that clear what I said? Is that clear what we can do to save upon the time complexity? So the entire idea is whenever you are solving, just store it somewhere. Cool. So now if I want to store solutions of subproblem, okay, then first thing that I should do is I should define my subproblem uniquely. Okay, I should define my subproblem uniquely. So this is very important thing, probably the most important thing behind DP. Define subproblem uniquely. Can somebody tell me how can I define a particular subproblem of Fibonacci uniquely? How many identifiers do you need to identify a unique Fibonacci number? Actually, you just need one identifier, and that is which Fibonacci number you want. So let's say I am saying f of 3, then this 3 is an identifier which is talking about third Fibonacci number. Okay, which is talking about third Fibonacci number. So guys, be very careful about what I'm trying to say over here. In some cases, in some problems of DP, in fact, in most problems of DP, you will find that you need more than one identifier to define a unique problem. But here, since it's a very basic problem, you can see that you just need one identifier. Okay, and that one identifier that uniquely identifies a problem is also called as a state. So this is the state of any problem in the DP. And since any unique problem is being identified by just one state, such kind of DP problems are called as 1D DP problems. This is one-dimensional DP problem because the problem can be represented by just one variable. That's it. Is that clear what I just said? This concept is going to be used across all the, the different kind of 2D DP, 3D DP. So the first thing for you would always be to identify how many states are uniquely identifying a problem. Once you do that, okay, I'll do that for you, Mayank. So here you can see, can I say that f of I, which is ith Fibonacci number, will always be different from f of j. And f of I uniquely identifies solution to ith Fibonacci number. Can I say that? Can I say that? Yes. So the only identifier that I need to uniquely define a problem for Fibonacci case is just one identifier, and hence this is 1D DP because every problem has just one state. Okay. So Akshay, is that clear now what I said about state? Identifiers required to define a problem. Cool. So if you understand this perfectly, now what we can do is we can just go ahead from here that since my problems are being identified by a particular identifier, what I will do is I will create some storage to store their solutions. Okay, some storage to store their solutions. So let's say I create a solution array. Okay, a solution array of size n. Okay. So I create a solution array of size n, and solution of I is going to store the value of ith Fibonacci number, if at all I have solved that. Okay. Now, this additional thing that I am going to use to store the solution of already solved problems, this is called as additional space, and this is also called as memo. So you guys might have used memos in your mobile phones. So this kind of technique where you use some additional data structure is called as memorization. Now for memorization, you can use different data structures. You can use map also, you can use maybe if required linked list also. But in context of this problem, a simple array can act as my memorization data structure. What is memorization data structure? Nothing, just extra memory where I will be storing the solutions of previously solved subproblems. Is that clear? How many of you understood this memos thing? Why do I need memos and how to define memos and all? Okay. Now another thing that should come to your mind is that how to decide how much space do I need? How to decide how much space do I need, and how to decide which kind of data structure do I need? So if you look carefully over here, in the process of finding nth Fibonacci number, how many distinct subproblems can you think of? How many distinct subproblems can you think of while you are solving for f of n? Just n distinct subproblems you can think of, not more than that. Because f of n will never call something which is greater than n. It will call something which is always lesser than n. So the value of this variable will fluctuate from 0 to n only. Okay, since it fluctuates from 0 to n only, I can easily comment that I need a memo whose size is order n and not more than that. So basically the size of your memorization data structure is defined by number of different unique problems that you will probably solve. Is that clear? How many of you understood how to decide the size of memorization data structure that you have to use? Okay, anyone having any doubt till here? These were really, really simple things without which you can actually not work. Okay, cool. So if anyone has any doubt, you can type in your comment here and I'll be able to address that. Okay, cool. Looks like all of you are thorough with this. So let me move ahead. Now let's solve the actual problem. That now we want to make that Fibonacci code, Fibonacci recursive code, a lot more efficient. So as I said, what I'll do, I'll create a memorization data structure, which will be my array, memorization array of size n. And initially I'll make every element equal to null. Okay. So find out has a doubt. So sorry, I didn't get your name. Can you just quickly type in your doubt? What is it that you want me to repeat so that I can quickly repeat that? Solution. Okay. So did you get the concept behind memorization data structure, that why do I need memorization data structure? Did you get that? Just say yes or no if you got that or not. Okay, cool. Now, what I'm trying to say from here is that since I need a memorization data structure, and since I know that at max, there can be n different problems. Yeah, we are doing some experiments with light, and whichever would be best, that we would continue with. So don't worry about that. So since I know that there can be at max n different subproblems, I am going to declare a memorization array of size n and not more than that. Is that clear now? Why this solution array, which is my memorization array, is of size n? Is the video better now? Is the video better now? Just say yes, those of you who can see it better. Okay, great. Cool. I think most of them are having this video as better. Cool. So what I'll do is initially I'll just initialize all the solutions as null. So this basically signifies that I have not solved any problem. I don't know the solution of 0th Fibonacci number. I don't know the solution of 5th Fibonacci number. I don't know the solution of 7th Fibonacci number. I don't know anything at all. Okay. Now let's rewrite the same code again to get the, let's say, xth Fibonacci number. Okay. So guys, you'll help me do that. So see, first thing that I can write is my termination condition. First thing would always be termination condition. So termination condition never takes more than order one time. So just let it remain as it is. So if my x is lesser than 2, I can simply return x, because Fibonacci of 0 is 0, Fibonacci of 1 is 1. Okay, cool. It has unique identifier, but if more than that, then how to identify that? Cool. So Ankit, let's say there is a problem which is being identified by I and j. Okay, there is a problem that is being identified by two identifiers I and j. If 100 values of I are possible from 0 to, let's say, 99, and similarly 100 values of j are possible from 0 to 99, I can say that I need 100 into 100 amount of space, which is 10 raised to power 4 amount of space. Is that clear? Because every combination of I comma j would signal a different subproblem. Is that clear? Is that clear how, depending upon the different values of state, you can comment upon how much of memorization space do you need? Okay. Cool. These things will become obviously more clear as you progress on this path of dynamic programming. Cool. Now what should I do? So guys, this was my termination condition. Now what should I write? So guys, now either of the two things could have happened. First thing, that either I would have already solved for this x, or I would have not solved for this x. Now, if I would have solved for this x, then solution of x would not be null. Solution of x would not be null. So let me just check that. So else if I see that solution of x is not equals to null, if this is not null, that means I had solved that somewhere before. So I can easily just return solution of x. Okay. Cool. Now, if let's say you bypass this else if also, if you bypass this else if, that means what? That means that you have not yet solved for solution of x. If you have not yet solved for solution of x, that means you need to solve for it, right? Is that clear? Can I just hear a yes or no? What I said is clear or not? Okay, that means I have not solved for this. Okay, so what I'm trying to say is that, see, initially I marked all the values in solution array as null. So this denotes that I have not solved for 0th Fibonacci number. See, this solution array, you can look like this. That from 0 till n. Everything is null, 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 null. So this basically says I don't know the answer of any Fibonacci number. Okay. Now in this recursive code flow, once let's say you have solved for this slot, you put the value over here. Let's say that is alpha. You put that value over here. Now whenever your recursive call is made for this again, you just simply check whether this is not equals to null or not. If this is not equals to null, you simply return this. Otherwise, you will solve for it. Okay. Is that clear now what I tried to say? Okay, so this was corresponding to what I said. If I have solved, I would return it. Now, if I have not solved, so you will move on to else. If I have not solved, then what should I do? There are two very, very important things to be careful about. If I have not solved, then what should I do? Then I should first solve it, and not just solve it, but also store that solution in the memorization array. So if I have not solved it, I will call Fibonacci of x minus 1 plus Fibonacci of x minus 2. And whatever value comes out from here, I would map that to solution of x, and then I would return solution of x. Okay. Guys, this is really important, that if you have not solved, then don't just solve, but also store it, because until unless you store it, it cannot be reused via this. Is that clear what I just said? Just say yes, those of you who are clear with this. So guys, this is the way in which you can make a recursive code more optimized. How you can make it more optimized? By using another memorization data structure. But before you move on to this kind of thing like memorization data structure, first you should be very, very comfortable in defining uniqueness of a problem. It is defining the state. Once you define a state, you define your memorization data structure, and then you solve, and then you store, and then you return, and so on. Okay, cool. Now guys, see, when this code flow actually works, how are things going to look like, that I would like to tell you. So pay a lot of attention. So let's say I start with Fibonacci of n. So sometimes, can somebody tell me that in order to solve for n, how many function calls will happen? Can you tell me in terms of n, how many function calls are going to happen if I invoke f of n from main function? Exact number of function calls. Are you sure this is going to be n, or do you think this is going to be something more than n or something less than n? Okay, so let us take a look at that. This f of n will invoke f of n minus 1 and f of n minus 2, right? Now, this will be ballpark because this function would execute first. F of n minus 1 would invoke f of n minus 2 and then f of n minus 3. Guys, you know, one thing to note over here is this function call will never explode. How many of you see that? This function call will never explode because this would be solved as a part of solving this. And the same thing is true for this. This would be solved as a part of solving this. So this will invoke f of n minus 3, which gets solved. Now, f of n minus 4 would be solved as a part of solving f of n minus 3. So it will go on, and this branch would go on till, let's say, f of 1. Is that clear what I said here? Is that clear what I said? That this thing would be solved as a part of solving this. And this is true for all the nodes. Even in this node, you can see this would be solved as a part of solving this. This would be solved as a part of solving this. So corresponding to these function calls, my else if branch would get invoked, which would just find the solution of this because this was solved here, located somewhere here, and it would return it. So basically this length would almost be order n. This length is n. And these things which are coming from each of them are also almost n. So this is going to be order of 2 into n. So I will not have more than 2 into n function calls. Is that clear? How many of you understood it? That to be very, very exact, this is going to be 2 into n function calls and not more than that. What about others? Is that clear? How is it exactly equal to that? Okay, cool. So Now let's comment upon the time complexity and space complexity of this. So the time complexity is equal to number of function calls that you are doing, because every function call finishes in order one time, assuming the fact that sub problems are already solved. So time complexity is almost order n. And space complexity means how much extra space you are using. So how much extra space are you using? What is the size of your memorization array? That too is order of n. Okay, cool. So guys, this entire thing that we just did over here is called as our top bottom DP. Top bottom DP. Why top bottom DP? Because you start with the intention to find the value of nth Fibonacci number, which is you try to solve the largest problem, and from top you go until bottom, and then the way functions return their values, you come from all the way from bottom till top. So this is a top bottom DP. This is a classical top bottom DP. Top bottom DP is nothing but recursive code plus memorization. So recursion plus memorization is simple top bottom DP. How time complexity is order n. Okay, how many operations have you done? How many operations have you done? How many function calls have you made? You have just made 2 into n function calls, right? And not more than that. So I can easily say that number of operations that I am doing is just 2 into n. 2 into n is nearly n. So the time complexity is order n. Is that clear? Okay, cool. Yeah, so guys, did you understand what I meant when I said top bottom DP? Top bottom DP is recursion plus memorization. You write a recursive code and then you memorize it. That's it, nothing else. Okay. Okay, we'll discuss that now immediately. So guys, since you have heard something called as top bottom, reverse of that also exists, which is bottom top. And guys, you have been solving this problem since your childhood, or maybe since your first year. How space complexity is, and somebody is asking. Space complexity means how much extra space you are using. How much extra space you are using. So if you take a look over here, I have used extra space corresponding to my memorization array size. And my memorization array has a size equal to n. So the space complexity is order n. That is the extra space that I'm using. Is that clear? Cool. Of course, those of you who were there in recursion's webinar should be able to relate that recursion also uses its own stack. Is it not? Recursion also uses its own stack, is it not? So yeah, so that space would also come. But what would be the maximum size of stack that you would ever get? Maximum stack size is the height of this recursion tree. Maximum function calls that you ever have at any point. That is also going to be order n. So order n is the extra space that you yourself have declared. And another order n is the extra space that recursive function call has ended up consuming. Is that clear? Are you able to clearly distinguish between the two order n spaces? First, that I myself have declared, and second, that my system ended up using as a part of recursive calls. Cool. Yeah, so yeah, what I was saying was that another approach to solve these problems is using bottom top DP. Okay, so what is bottom top DP? Bottom top DP is very simple enough. So what happens in bottom top DP is that if you can think of top bottom, you can easily convert that into bottom top. Whatever termination condition you write, termination conditions are corresponding to large problems or small problems. Can you tell me that? Termination conditions are corresponding to large problems or small problems. They are corresponding to smallest problems, okay? So bottom top DP says that, hey, first initialize the value of smallest subproblems. So that says that, let's say I declare my solution array of size n. So it says that make solution of 0 as 0 and make solution of 1 as 1. And now start building the value of, start fetching the value of Fibonacci numbers starting from I equals to 0, I equals to 2 till n. So what I can write over here is, for my I varying from 2 till n, I can simply write this code. Solution of I is solution of I minus 1 plus solution of I minus 2. I can comfortably write this because I am populating this solution array in a sequential fashion. So I initialize solution 0 as 0, solution 1 as 1, and now I can confidently vouch for this because I know the two values that come before, that are required to be there before. So this would be 1. Similarly, I can confidently vouch for this because I know these. I can vouch for this because I know this, and so on. So this is bottom top DP. Bottom top DP. Is that clear? Is that clear, the bottom top DP? Okay, now if you take a careful look over here in this bottom top DP, what is going to be your time complexity? What is that time complexity over here? How many operations do you do? So order n operations to be exact. Order n operations. You run a loop from I varying from 2 till n. And what is the extra space that you ended up using? The extra space is also order n, okay, for this solution array. Okay, if you look at it a bit wisely, you will be able to understand that you don't actually need this much space while solving this question in bottom top manner. How many of you can solve this question using constant extra space? Can you do that? So the answer is you can actually do that, because let's say I am trying to find the value of this. In order to find out the value of this, I just need the value of this and the value of this. So if I just maintain two variables, let's say first and second are the two variables, and I just keep changing their values, I'll be able to comment upon the next value that is going to come. Okay, explain bottom top once more, please. Okay, so bottom top is something, in bottom top what you do, you initialize the solution of smallest subproblems. Okay, smallest subproblems here are Fibonacci number, 0th Fibonacci number and first Fibonacci number. Then you solve for the next greater problem, then next greater problem, then next greater problem, and eventually you end up solving the largest problem. So you build your solution from bottom to top. That is why this is called as bottom top solution. Is that clear? Did you get bottom top? Initialize the, and one thing to note over here very clearly is that bottom top is not recursion. Bottom top is not recursion. It is iteration. You just need to run a for loop, and that for loop runs sequentially, and because you are populating the values also in a linear fashion, very much sequentially. Is that clear? Now the bottom top, is that clear? Just say yes, those of you who are clear with this. Okay, cool. Now one thing that I wanted to tell you in bottom top, since you know the good thing about bottom top here is that in order to find out the next value, you just need the previous two values. Okay, so what you can do is you can just keep two variables, let's say first and second, and keep on just changing their values as you move ahead. Okay, and then you will be able to eventually come up with nth Fibonacci number. So using bottom top, I can cut down on my extra space from order n to order 1. Is that clear? How many of you are getting this? Just say yes, those of you who are clear why bottom top is allowing me to cut down on my extra space. So guys, now please don't remember it, don't mug it up. This is just one example where bottom top is performing better than top bottom in terms of space, but it is not always necessary. For some problems, top bottom is more efficient. How to code it? You can code it very easily. I'll just quickly write the code for this. So let's say what you can do is you have two variables, first and second. So let's say my first is initialized to 0. My second is initialized to 1. This means 0th Fibonacci number. This means first Fibonacci number. And then I run a loop from 2 to n. And what I can do is my current value that I'm trying to get, that would be the sum of first and second. Okay. And now my first should be equal to second and second should be equal to current. So how do I do that? First becomes equal to second and second become equals to current and so on. When this loop is over, the value of current would be equal to the nth Fibonacci number. Is that clear? Is that clear? Yes, no, how can you code that? Sir, why can't we use recursion for bottom top by making termination condition as end of array. You can do that for sure, but you don't actually need to do that if you understand it. Because see, in recursion, what happens that in recursion, the way you are populating the contents of your memorization data structure, that is not sequential. You don't know when which slot is getting filled. Okay, but using iteration or bottom top approach, you fill it in a linear fashion. So if at all you are doing that, you don't need recursion to recursive code to be written and end up using some extra space because of its own recursion stack and all. Okay, so that is why you stick to iteration when you are actually building a bottom top based solution. Okay, cool. So could you all understand that what was the difference between top bottom and bottom top, and the pros and cons of both the approach? In which terms, which one was better? Yeah, but don't mug it up that bottom top is always good. It is not necessary. It depends upon the problem. Okay, guys, so now what I'll do is I'll take a problem, really basic problems. Some of you might have heard of it, but it would be worth trying. Okay, so how many of you are clear with everything covered till now? Just say yes, those of you who are clear with everything. All the concepts of DP, bottom, top, top, bottom, memorization, how to define a unique problem and all. Okay, that's great. So guys, now the question goes like this. It's interesting for those of you who have not yet heard of this. So you have been given 2 cross n. I would request others to remain silent. If you know the solution, please keep it up to yourself. You can privately message it to me if you want to message the solution. So you have been given a 2 cross n board. Okay. So there is a board whose length is fixed. Length is 2 units and breadth is given by a variable. That n can be anything. N can be 10, n can be 1. It can just be anything. Now what you have to do is you have to perform tiling of this board. Okay, you have to put tiles in this board. Now we have following kind of tile. Our tiles have this particular dimension only, which is 2 cross 1. Okay, 2 cross 1. Now you have to tell me number of different ways of tiling the board. How many different ways are there in which you can tile this board using these tiles? So how many of you understood the problem? Just say yes, those of you who are clear with the problem. This is not exactly a combinatorial problem. This can be, so try to use the concept of DP somewhere here. Okay guys, so let us take n equals to 2. So if n is equals to 2, my board is a 2 cross 2 board. Can you tell me how many different ways are there to tile a 2 cross 2 board using a 2 cross 2 tile? How many different ways are there? Okay, so most of you are saying 2, and that is right. Are you saying that first way could be that if this is a 2 cross 2 board, put first 2 cross 1 tile over here and put another 2 cross 1 tile over here? Are you saying this is the first way? Let's say yes. Is this the first way of tiling? And if you are saying this is the first way of tiling, are you also saying that the second way of tiling is that this 2 cross 1 tile, I'll flip it. I'll flip it and then I'll tile it like this. So this is 1. And then another tile can come over here by flipping it. So are these 2 ways clear? Just say yes, those of you who understand that these 2 ways are clear. Okay. Now guys, we'll just try to think how I can leverage DP over here. So guys, what was the first basic symptom of DP that I talked about? What was the first basic symptom? How do you realize whether a problem can be solved using DP or not? Okay, first thing was that optimal substructure. That optimal substructure is a tough word. I just mean to say that solution of a larger problem depends upon the solution to smaller subproblems. That is first thing. We'll try to check whether that symptom is here or not. And second thing that you will understand over here, that is very, very important thing, that is called as element of choice. Okay, that is called as element of choice. Now, what is element of choice? That we will understand over here. For that, focus your 100% attention on the board. So element of choice means that, guys, let's say I want to start solving this problem. Okay, let's say this is our 2 cross n board. Okay, and I want to start solving this problem. So I just pick up this tile and I want to start my process of tiling. Do you have choices or do you just have one choice? To start your business with first tile, do you just have one choice or do you have multiple choices? And if you have multiple choices, what are those choices? So Tushar says that I just have one choice. So Tushar means to say that, hey, this is a 2 cross 1 tile. I can just put it over here as it is. But is there any other choice? There is one more choice. So see, first I'll go by Tushar's choice where he'll put this vertically. Okay, by vertically I mean to say he'll put it as it is. So if he puts it as it is, it becomes something like this, that this 2 cross 1 portion has now been tiled, and now what remains is n minus 1. Okay, but if I would have chosen this to tile it in a horizontal manner, then let's say I would have done something like this. That this is 2 cross n board. If I would have tiled like this, then I have consumed 2 length over here. Then the only choice that I have for this portion is to put another tile in the same way over here. Is it not? Is it not? So these are the 2 ways in which I can start my process of tiling. First way is put this thing horizontal, put this thing vertically, and then just focus your attention on remaining part. Second choice is put it horizontally. So if you put it horizontally, you need to put another one also horizontally, and then focus on the remaining n minus 2 part. Is that clear? This is for horizontal. Is that clear? How many of you understood these 2 choices? So whenever there are multiple choices and you need to venture out into all those different choices, that is called as element of choice. So if you see a problem where there are different choices that you can make, it might be possible that DP can come in handy over there. Another thing to note over here very carefully is that here when you are applying element of choice, your problem size is reducing. What I mean by that is once you have put 2 cross 1 tile over here, you just need to know how many different ways are there to tile this n minus 1 cross 2 portion. And how many different ways are there to tile this n minus 2 cross 2 portion. Is that clear? Is that clear that how your problem is getting reduced? Okay, I'll repeat that again. So see, can I say that from this function call, everyone focus on the board, from this function call, I'll get all those kinds of tiling whose initiation is with this kind of tile. Can I say that? Yes, no? When this recursive call explodes, I'll get all those kinds of tiling whose first one is like this. And can I say that from this, I'll get all those kinds of tiling. I'll get different, but one thing that would be common in each of them would be that they will be having their initial border like this. Is it not? Is it not? So can I say that all solutions over here would be different from all the solutions that I get from here? Can I not say that? All solutions of the left part would be different from all solutions of the right part. So I'm not even repeating the different orientations of tiling. I'm just ensuring that I get different set of answers from here and different set of answers from here. Now the same thing that was true for this would be true when I do for this also. So what I mean by that is when you are off to tiling the remaining n minus 1 portion, what is going to happen in this remaining n minus portion? Again, the next tile, either after this You can put another one like this, and then the space that remains with you is n minus 2. Or what you could have done is, after this, you could have placed the tile in this manner. Okay. And then you would have been remaining with n minus 3. Okay, now I can easily say that all solutions that I am going to get from here start with this, and all solutions that I am going to get from here start with this. So nothing from here would be found here, and the vice versa. Is that clear? What would happen in horizontal way if n is odd? Even if n is odd, nothing is going to happen, because this n denotes your length. This n denotes your length. So even if your n is odd, nothing is going to happen. If let's say your n was 3, if this is let's say 2 cross 3, if you put first one like this, okay, then 2 units are gone, just 1 unit of space is remaining here. You can put a 2 cross 1 over here, 2 cross 1 over here. Okay, you will not go for another horizontal second, you will just put a vertical and finish it over there. So it will take care of all the possibilities, whether you are moving on to remaining portion which is of odd length or even length. Is that clear? So first of all, do you all understand that how I am making different choices and venturing into solving smaller sized problems? Are you getting that? Making different choices and venturing into solving different smaller problems. Now, what would be the termination condition over here? Can you think of some termination conditions? For, let's say, can you tell me what will be the answer for n equals to 1? If n is equal to 1, then how many different ways are there? Just one way. For n equals to 1, answer would be 1. Okay. And also you can say that for n equals to 2, the answer would be 2, because we just showed. So that can be your termination condition. And then basically what you are doing, your function of n is calling function of n minus 1 and function of n minus 2 and summing them up. This fn minus 1 is telling me all those tilings that start with this, and this fn minus 2 is telling me all those tilings that start with this. There is no intersection at all. This goes on and on like Fibonacci, has some termination condition like how Fibonacci numbers have, and then I eventually get my solution. Is that clear? How many of you are able to say that Fibonacci thing in this? Total ways equals to sum of all function calls. No. Total way, f of n denotes, what does f of n denotes? F of n denotes that if the length is n, how many different ways are there? How many different ways are there? So whatever value gets stored in f of n, or whatever your function called to func of n returns, that is total number of ways for func of n. That depends upon func of n minus 1 and func of n minus 2. That is the only thing. Is that clear? Yes, no, anyone having any doubt? How this is? Okay guys, so tell me, what all are the things that you do? This is a very simple problem. So sometimes I've seen like people just mug it up like Fibonacci rule is going to work over here, but sometimes they're not able to answer conceptual things hidden in this. Some conceptual things hidden in this are that the moment you are making two different choices, that is guaranteeing that there is going to be no overlap at all. Okay, and the moment you are making some choices, you are automatically boiling down to smaller subproblems. Okay, so both things are happening. And if you, let's say you are solving it using recursion and you can memorize it the way we had memorized Fibonacci code, you will be able to solve it in order and time. And of course, you can do it using bottom top also. You can just put f of 1 as 1, f of 2 as 2, and keep on building till n, and you will eventually get your solution. Okay guys, so how many of you are absolutely clear with all the concepts that I have talked about in this? The different concepts, that the elements of choice you can make and how you populate the memorization array and everything. Cool. So now let's move on to another problem. So I'll take another interesting problem that you can think how to solve using dynamic programming. Okay, so code you can write on your own, right? This is just a Fibonacci code with slightly different termination conditions. Okay, so you all know what a bit string is? Does everyone know what a bit string is? So bit string is a string that just contains bits. So any character could either be 0 or 1, that's it, nothing else. Is that clear? As simple as that. A string of bits is a bit string. So the question is that you have been given an integer n. Now you have to tell me count of bit strings without consecutive ones. Count of bit strings without consecutive ones. So there should be no adjacent ones. So let's say my n is equal to 2. So can you tell me how many bit strings of size 2 will be there? How many bit strings of size 2 will be there? Can you tell me that? I can think of just 4 bit strings, 0, 0, 0, 1, 1, 0, 1, 1. Is that clear? Okay. Now the question says number of bit strings without consecutive ones. Is there a bit string in these bit strings which has consecutive ones? Yes, this is the one. So if I cancel this, I'll say that there are 3 bit strings of size 2 which don't have consecutive ones. So I repeat the question, given n, you will have to tell me that out of all the bit strings of size n, how many such bit strings are there that do not have consecutive ones? How many of you understood the question? Just say yes, those of you understood the question. So if you understood the question, just tell me solution for n equals to 3. How many bit strings of size 3 can you think of that do not have any consecutive one? And it would be great if you can type those bit strings also of size 3 without consecutive ones. Okay, so Sunil says 5, Gayatri says 4, Harshal says 8. Okay, so for size 3, I think I just have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 0, 1. How many of you can just think of these 5 bit strings of size 3 that follow this rule? Just say yes. Anything else that you think of will have consecutive ones, is it not? Anything else will have consecutive ones. Okay, so how do I solve this question? Anyone who would like to take a try at solving this question, maybe suggesting some approach that I can do something like this or that to solve this? Solve for n equals to 2, okay. Okay, think of it like this, that if you know the answer for n equals to 2, can you tell me the answer for n equals to 3? Okay, that is right. If previous is 0, then don't worry, like Fibonacci. Okay, Sunil, can you elaborate a bit more, like how exactly like Fibonacci? Okay guys, so I want all of you to be very, very robust in doing this on your own. Just take out your notebook, and this is the answer for n equals to 3. Okay, this is the answer for n equals to 3. I want all of you to type all the bit strings for n equals to 4 on your notebook. For n equals to 4, how many are there? Can you do that? Try it out. So which part of DP are we doing? I am just trying to build answer for a bigger problem from answer for a smaller subproblem. I'm just trying to do that. So all of you try to take a shot at that, and then the moment you do that, automatically you will be able to, you know, think of the DP code behind that. Okay, so Kunal has pinged me few things. How many of you are able to do that? How many of you feel that there are 8 such bit strings of size 4? How many of you have got 8 bit strings of size 4 which are following this rule? Okay, cool. That's awesome. So guys, let's try to do that. So let's say everyone focus on the board now. This is really, really important, and tougher variations of this problem are asked in interviews on a regular basis. So focus your attention on the board. So any bit string of size 4. Let me consider any bit string of size 4. Okay. The first 3 bits would be forming a bit string that comes somewhere from here, is it not? That comes somewhere from here. So what I am intending to say is, if I know the bit strings for n equals to 3, can I germinate the bit strings for n equals to 4? The answer is yes. Now how? Look at the board. So see, first split it into 2 categories. First category is the ones that end with 0, and second category is the one that ends with 1. So how many are ending with 0? This, and this. So 0, 0, 0, 0, 1, 0, and 1, 0, 0. And how many are ending with 1? This and this. 0, 0, 1 and 1, 0, 1. Okay. Now, since I am trying to create bit strings with length 4, I can either append the next character as 0 or 1. Now, can you tell me one thing? From all those bit strings that are ending with 0, I can germinate 2 more bit strings for sure. First one that ends with 0, and the second one that ends with 1. Is it not? Is it not? But out of all those bit strings that are ending with 1, can I generate 2 child? One ending with 0, one ending with 1? No, because the moment you generate the one that ends with 1, this rule will get violated. You will have adjacent ones. Okay, so from here I can just germinate 0, 0, 1, 0 and 1, 0, 1, 0. Is that clear? How many of you understood that? Just say yes if you are clear with this. Okay, can I rest assured of the fact that there will be no repetition in this and this? Can I rest assured of that there will be no repetition? If yes, how? How can I stay very, very comfortable that there will be no repetition? Because the second last character here would always be 0, and the second last character here would always be 1. So nothing in this would be able to match anything in this. Okay, and also in this, it would never happen that that something is equal to the other thing, because out of this, the 2 that are getting birth, first one ends with 0 and the other one ends with 1. And of course, across these, you can clearly see that since they are taking birth from different parents, there is no chance of repetition happening. Is that clear? How many of you can see that there is no repetition that is going to happen? Just say yes, those of you are able to see that. Okay guys, now one thing to understand over here is that, again, now I know that there are 8 bit strings of size 4 that follow the rule that I was talking about. Now again, you can just club all those that are ending with 0. The ones that are ending with 0 are this, 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 and this. So these 5 will create how many children for n equals to 5? These 5 bit strings that you can see will create 10 bit strings, 10 such legal bit strings for n equals to 5. Okay, so I get 5 into 10, 5 into 2, and these which are ending with 1, 3 of them are there, they will be able to create 1 child each only. So plus 3 into 1. So 5 into 10, 2 is 10. So 13 bit strings would be there for n equals to 5. Okay, how many of you followed what I just did? Just say yes, those of you who were able to follow that, how I am able to deduce. Okay, Akshay, can you tell me what is it that you did not get? Which part did you not understand? I'll help you understand again. Internet unstable, okay. The other guy, find out. Yeah, what was it that you didn't get? So all that I'm trying to say is, let's say I know for n equals to 3, these bit strings are there, okay? Now, there are 2 categorizations that I'm doing. First categorization is ending with 0. So ending with 0, these are the ones. Ending with 1, these are the ones. So those that are ending with 0 have potential to give birth to a 4-sized bit string, and they can either end with 0 or end with 1. Okay, why am I not worried? Because the last character is 0. So whether 0 comes after 0 or 1 comes after 0, my rule is not going to get violated. Okay, but out of all those bit strings that are ending with 1, the next character has to be 0. So they'll just germinate 1 child each, unlike the other one. Is that clear? Is this much clear? Yes, no, is this much clear to all? Okay. Now guys, if you understand one thing over here, there are 2 identifiers that are involved over here. 2 important identifiers. First identifier is that if I want to solve for n, is just this much sufficient that I know the solution for n minus 1? Is just this much sufficient that I know the solution for n minus 1? Yes, no? How many of you feel this is sufficient? How many feel this is not sufficient? The answer is this is not sufficient. Somebody says me that, hey, for n equals to 3, there are 5 bit strings. Just from that 5, can I say that for n equals to 4, how many will be there? Will I be able to say? The answer is no. I will have to know about the categorization also. And by categorization, I mean to say that how many bit strings of size n minus 1 are ending with 0, and how many of size n minus 1 are ending with 1. If I know this, then can I comment on this? If I know how many of size n minus 1 are ending with 0 and how many of size n minus 1 are ending with 1, then can I comment on this? Yes, then I can easily comment on this. Then this will simply be 2 times of this, because after 0, 0 can also come, 1 can also come, and 1 times of this. Okay, so this is my solution for n. Now, one thing to be very careful about is that you would also want to solve for n plus 1. You would also want to solve for n plus 1. So basically within this n also, you would want to find category, and that you can do very easily. That you can do very easily. How you can do that? So let me just show that to you. So let's say you know how many bit strings are there of size n minus 1 ending with 0, and how many bit strings are there of size n minus 1 ending with 1. Now tell me, how many bit string of size n will be there that end with 0? Who will tell me that? How many bit string of size n ending with 0 will be there? So those that are born from here and those that are born from here. Is it not? Is it not? This will give birth to bit strings of size n ending with 0, and this will also give birth to bit strings of size n ending with 0. Are you getting what I'm trying to say? This is just mathematical formulation of what I have done over here. You can see all those ending with 0 have given 1 birth each to bit string ending with 0 and size n, and same for those ending with 1. So this is this plus this, n minus 1 comma 0 plus n minus 1 comma 1. and bit strings of size n ending with 1, what will it be? Will it simply be how many bit strings of size n minus 1 were there that were ending with 0? Can I write that? Can I write that? Just say yes if you are able to understand that. Number of bit strings of size n ending with 1 will simply be equal to the number of bit strings of size n minus 1 ending with 0. Okay, so Shivam, can you tell me what is it that you didn't get? Which part did you not understand? Just type in, could you follow all these? Could you follow this illustration that I did over here? Mathematical one, okay. How is this defined? How is this n comma 0 being defined? So that is a good doubt that you have. It is very, very important to understand what does this pair mean. This means how many bit strings of size n end with 0, okay? So let's say I know how many bit strings of size n minus 1 are there that are ending with 0. So I know that number of bit strings of size n minus 1 ending with 0 will germinate one child each that end with 0 and have a size n, okay? So this comes from here, the birth being given by here. And also if I know number of bit strings of size n minus 1 that end with 1, they will also give one birth each to the bit strings that end with 0. So this is coming from the children that are being germinated from here. And this is coming from the children, these children that are being germinated from here. Is that clear now? That how n comma 0 is getting defined? To say yes if you got it, or do you still have doubt? Similarly, do you understand this? That how many bit strings of size n are there that end with 1? So the bit strings of size n that end with 1 cannot take birth from the bit strings of size n minus 1 that also end with 1. Because repetitions would happen, repetition of 1 would happen, 1 would come after 1, okay? So they would be germinated only from the bit strings of size n minus 1 that are ending with 0, you can see. These ones are just germinating from these. And you can see that here the problem size is n in the LHS, and in the RHS the problem size is n minus 1. So basically a problem of larger size is related to a problem of smaller size. Is that clear? Just say yes if that is clear. How many of you are clear with this equation that I have written? So guys, don't see this as some tough mathematical equation. This is just logical. If you understand what I spoke, I'm just translating that into logic, okay? Cool. Now, if somebody asks me that how many valid substrings of size n are there, that will be nothing but number of bit strings of size n ending with 0 and number of bit string of size n ending with 1. Is it not? My actual answer would be number of bit strings of size n that end with 0 and number of bit string of size n that end with 1. Is that not? Yes, no. So basically what I am doing, that as I am solving for n, I am performing categorization. How many bit strings are there that are valid and end with 0? How many bit strings are there that are valid and end with 1? And so on, I keep on building my solution. The problem is that we can solve these problems on board, but very hard to write in terms of mathematical formulation. Don't worry, that comes with some amount of practice. And if you try it after the lecture is over, then you will be able to, you should be able to code it if you understood it over here. It's not that tough to code. Okay, let's get into other minute details. Other minute details are that, guys, here, how many identifiers are required to uniquely identify a problem? So unlike in Fibonacci I just needed one identifier. Here, how many identifiers are required to identify a problem? 2, is it not? 2. First identifier would be the size of the bit string, 4, 5, whatever. And second identifier would either be 0 or be 1. Is it not? Is it not? Second identifier would either be 0 or be 1. So there are 2 identifiers that I basically need to solve this problem. Okay, now let's say if I have to solve for n equals to 3, okay? Let us all just try to solve for n equals to 3. N equals to 3. So let's say I want to find out how many bit strings of size 3 are there that follow this rule, okay? So my function will have two states in it, okay? First, I want to find out how many bit strings of size 3 ending with 0 are there, and then later I will find out how many bit strings of size 3 ending with 1 are there. I'm ballparking it. I'll do this later, okay? First, let me do this, okay? So let's say if I have to do this, how many bit strings of size 3 ending with 0 are there? They all will be born out of bit strings of size 2, either ending with 0 or ending with 1. Is it not? If the third character has to be 0, the second character can be 0 or 1 also. Is it not? Yes, no, can either be 0 or be 1. What do you say about that? According to the rule, right? So what I wrote over here, f of n0 is f of n minus 1, 0 plus f of n minus 1, 1. So this can call f of 2, 0 and this will call f of 2, 1. See, understand the physical significance of this. F of 2, 0 says how many valid substrings of size 2 are there that end with 0. How many valid substrings of size 2 are there that end with 1. All of them can be appended with 0 and I will get all the valid substrings that are of size 3 and end with 0. Now let us take this down. F of 2, 0 will again, according to this, will be f of 1, 0 and f of, what do you say, 1, 1. F of 1, 0 and f of 1, 1. Now what should be the termination condition? Can somebody tell me about the termination condition? What will be the termination condition here? Termination condition would be that when my n becomes 1, what does this say? This is saying that how many bit string of size 1 will be there that ends with 0. Can you tell me how many bit strings of size 1 will be there that ends with 0? Just one, which is 0. Okay. So this is a termination condition. Whenever my n becomes equal to 1, I can just return what? I can just return 1 from there. And that 1 bit string is 0. Okay? Here, that 1 bit string would be 1 because this is saying how many bit strings of size 1 will be there that ends with 1. Okay? Now, f of 2, 0 needed this and wanted to add this. Okay, so basically f of 2, 0 is just going to append 0 at the end of this. So the solutions it is going to get is 0, 0 and 1, 0. Same thing here. F of 2, 1. How many branches would come from here? Can you tell me how many branches would come from f of 2, 1? F of 2, 1 depends upon what? If you take a look over here, f of 2, 1 depends upon what? It needs to know how many bit strings of size 1 will be there. How many bit strings of size 1 will be there that end with 0. So f of 2, 1 will call f of 1, 0. And when it calls f of 1, 0, tell me what happens. F of 1, 0, what is it going to return? F of 1, 0 is going to return 0. Okay. And then this will basically append 1 after this. Okay. And now when it comes here, this is sum of this and this, which is 3. So this appends 0, 0, 0, 1, 0, 0, and 0, 1, 0. So basically by making this call, I got all the bit strings of size 3 that are ending with 0. Similarly, by making this call, I will be able to get all the bit strings of size 3 that are ending with 1. Once I get that, I just need to add f of 3, 1 and f of 3, 0. That is my answer. Is that clear? How many of you got it? Just say yes if you got it. This sample dry run of this recursion tree. Okay, cool. That is why recursion is very, very important if you have to understand, dynamic programming. Cool. Now tell me one thing. Do you see problems getting repeated over here? Problems can actually get repeated over here, is it not? Because let's say I'm solving for f of n1, this will call, let's say I'm solving for f of n0, this will call f of n minus 1, 1, and this will call f of n minus 1, 0. Now it might happen that this f of n minus 1, 0 will call f of n minus 2, 1, f of n minus 2, 0. It is very much likely that this kind of function call is made in this part also. If you draw this further, you will see that problems are actually getting repeated. Can you see that? Can you see that? Can you explain for 3 consecutive ones at last? Sure. So if time remains, I'll let you know that. But if the time is not there, you can mail me that. I'll send you the explanation for sure. Cool. So yeah. So the problems can get repeated over here. So first thing, I need a memorization over here to solve this problem. Can you tell me the size of memorization array that I might need to solve this? What will be the size of memorization array? Who will tell me that? So basically, I need a 2D array called solution of size n cross 2. Because first dimension, which denotes size can fluctuate from 1 to n, and the second dimension would fluctuate in between 0 and 1 only. So my memorization array can be a 2-dimensional array of size n cross 2. That's it. Is that clear? Just say yes, those of you who are clear. Why do I need n cross 2 based memorization array? Yeah, so you can declare n cross 2 memorization array, and then you can easily write the recursive code to solve this problem. How many of you can write the recursive code to solve this problem? Just say yes, those of you who can. Write the recursive code now. Okay. Cool, great. Can you do this using, give it a shot, even if you're not so confident, you can write a code on your own, try out once, and then you can get back to me. You can even mail me your code. I'll be happy to put comments and suggest what could be better. Okay, can you solve it using bottom top? How many of you feel you can solve it using bottom top? So it depends. In some questions you feel like bottom top is easy. In some questions you feel top bottom is easy. But be very, very aware of the fact that your interviewer can put a constraint on you that, hey, solve it using this approach. Okay. Cool. So let's say I have to solve it using bottom top. How do I solve it using bottom top? So even that is very easy. So guys, what is my termination condition? Can you tell me my termination condition? Can you tell me my termination? I'll send you my email ID. I'll write my email ID. Don't worry about that. Okay. So what is the termination condition over here? Can somebody tell me that? When the string length becomes 1. Okay. So can you tell me what will be the value of solution 1, 0 and what will be the value of solution 1, 1? Can somebody tell me that? They will be 1 each, because what is the definition of solution 1, 0? Solution 1, 0 is defined as how many bit strings of size 1 are there that end with 0? Just 1, which is 0 itself. How many bit strings of size 1 are there that end with 1? Just 1, which is 1 itself. And this was 0 itself. Once I have these, can I solve for I varying from 2 to n? Once I have this, can I solve for this? Can I solve for this? Just say yes if you feel I can solve for this. That is very, very easy to solve, right? What I can do is that solution of I1. What should be the value of solution of I1? If I know the solution of I minus 1, 0 and solution of I minus 1, 1, can I solve for this? So if I know that how many bit strings of size I minus 1 are there that are ending with 0, then this value will exactly be equal to this, because 1 can be appended to only those bit strings of size I minus 1 that are ending with 0. Is it not? Is it not? Just say yes, those of you are following this. So solution of I1, can it be written in terms of I minus 1, 0? The answer is yes. So this will just be solution of I minus 1, 0. And can you tell me the expression for solution of I0? How many bit strings of size I will be there that end with 0? Knowing the fact that you have solved for I minus 1. what will it be? So all those bit strings of size I minus 1 that are ending with 0 can also be concatenated with 0. And all those bit strings of size I minus 1 that are ending with 1 can also be concatenated with this. So keep doing this on and on and on. And eventually you would have solved for I equals to n also. So eventually what you need to return is solution of n0 plus solution of n1. This tells how many bit strings of size n are there that end with 0 and how many bit strings of size n are there that end with 1 valid strings. Is the bottom top approach clear? Just say yes, those of you who are clear with this. Okay. How many of you can see that in this bottom top approach you can cut down on space complexity? How much space complexity is there? Can somebody tell me that first? How much extra space am I using over here? 2n, because size of my 2n, to be exact 2n. The size of my memorization data structure is 2 into n. But can you cut down on this space just like the way we did for Fibonacci? Can you actually cut down for this space? The answer is yes. Actually, you can cut down on this space. Now let's look at that how. Let me just draw this 2D array. So guys, this 2D array is something like this. 2 cross n, something like this. Okay, now hold on. See, when I am solving for I just need answers for I minus 1. Is it not? When I am solving for I just need answers for I minus 1. So let's say I want to solve for this. Okay, then I basically want to populate this and this. To populate this and this, I just need to know about this and this. Do I need to know about these? Do I need to know about these? No. The answer is no. So what you can do is you can just keep two variables. See, coding part I leave up to you because right now I have one more problem that I would want to discuss. So you can just keep two variables and keep on changing them. Okay, keep on changing them and then you will be able to get the new ones. You don't actually need to keep track of all these. So again, you can see that here also bottom top is performing better in terms of space complexity. Okay, but you could not have been able to do this in recursive approach. Could you have been able to do this in recursive approach using the two variables? The recursion tree diagram that I was drawing, could you have just used two variables to do that? Yes, no? Actually, no, it would not have been an easy task for you to do because how recursion is populating different values, you don't know. But here in this iteration based logic, bottom top, iteration based logic, see, be very, very familiar to these terms. When there is just a loop, that is bottom top. When there was recursion plus memorization, that was top bottom. Okay, cool. So how many of you are clear with both the bottom top and top bottom approach over here? Just say yes, those of you who are clear with this. Okay, cool. So guys, I just want to know one more thing. Those of you who are maybe studying DP for the first time, how many of you are now able to understand these things like top, bottom, bottom, top memorization? Are you getting a hang of those? Just say yes, those of you who are able to understand that. Okay, so that's really great. But when you go back, please ensure that you solve these problems. You try out these coding problems on your own, on your code editor. Then it will so happen because DP has very simple concepts. It's just that the problems have large variation, but we have taken care of that also. We have compiled a list of premium questions which cover all kind of DP, and if you do those problems, then it's like you're more than prepared. Okay, I'll ping you the link. Don't worry about that. Cool. So guys, I have one more problem. We can do that also. So let's do that. That is again a popular interview problem. So it's a good idea if we all. So this will be last question for the day, and then we'll be done. So guys, type in your chat box what are the two symptoms of DP that you have understood now. What are the two symptoms of DP? Everyone, I have spoken about it multiple times. What are the two symptoms of DP? Okay, so the first symptom of DP was what? Element of choice. And the second symptom of DP was what? Second symptom was optimal substructure. Even in this problem, bit string problem, we had two choices, right? Either the last bit could be 0 or it could be 1. And then the moment you make choices, you venture into an input space that is smaller than the previous input space. So you automatically come to optimal substructure thing. Is it not? So realizing these things is very important. So again, I'm going to give you a problem where you have to search for just these two things. First thing, element of choice, and second thing, smaller subproblems, okay, which is optimal substructure technically. Okay, so the question goes like this. So I'm going to define some encodings for you. Okay, I'm going to define some encodings. Let's say these encodings are like this, that capital A is 1, capital B is 2, capital C is 3, so on and on and on. So capital Z would be what? Capital Z would be what? It goes on and on like this, it would be 26, right? So let's say I have defined this kind of encoding. Now, what I want to do is that I have been given a string, and that string contains either digits from 0 to 9, 0, 1, 2, so on till 9. That string contains digits from 0 to 9. Now you have to tell me different decodings that are possible. Different decodings that are possible of the given input string. So let me take an example. So let's say my string is just 7. If my string is just 7, I can be pretty sure that, hey, this 7 was for G, A, B, C, D, E, F, G, G is for 7. So there is just one decoding possible, and that one possible decoding is just G. But if let's say my string was something like 12, can you tell me how many decodings are possible? For 12, how many decodings are possible? Okay, somebody is saying 3 and some of you are saying 2. So can you print those decodings for me? If you're saying 3, how is it 3? If you're saying 2, how is it 2? So if I were to decode this 12, what I could have done is either I can consider this 1 as A. If I consider this 1 as A, I would be forced to consider this 2 as B. So first decoding could be AB, where A is for 1 and B is for 2. And second decoding could be that I could have considered this 12 as L. That's it. So these are the two decodings that are possible. Is that clear? How many of you got the two decodings that are possible of the given input string? You say yes, those of you are clear with the two decodings of this. Okay, so anyone having any doubt in this, that how the different decodings are being talked about? Okay, let me ask you one more example. 123. How many different decodings are there for 123? 3 decodings can be possible for 12. Okay, Akshay, what are those 3 what is that third one that you feel I have missed out here for 12? A, B, L. No, see, the moment you sacrifice this 1 for A, how can you generate an L? Because L is equal to 12. What remains is just 2. You will have to consider this 2 for B, and what you get is AB. Okay. Other choice could have been you don't sacrifice this 1 for A. So you merge this 1 with 2 and you consider this as 12, and 12 is L. Is that clear? Okay. Yeah, for 123, how many decodings were possible? For 123, how many of you got that these are the decodings that are possible? If I consider this 1 as A, 2 as B, 3 as C, I get ABC. Very good. If I consider this 1 as A, I can consider this 23 as W. And the last one is if I consider this 12 as L, I consider this 3 as C. How many of you got these three possible decodings? Just say yes, those of you got it. Okay, so the question is not asking you to print all these decodings. The question is just asking you to answer three, that how many different possible decodings are possible from a given input string. Now, how many of you are clear with the question? Just say yes, those of you who are clear with it. Is the question clear? Yes, no. Okay, how do we solve this? Two things. What are those two things that you have to always think about? Element of choice, and second thing, optimal substructure or smaller subproblems. Guys, one thing that you also should understand is, in the last problem when I was drawing, let's say, function structure like f of n0, this had a physical significance. Whatever function call I was making and whatever inputs were getting passed to it, that had a physical significance, is it not? Like physical significance was bit strings of size n that strictly end with 0, things like those. So make a habit of that, that every function you should be able to think of it like in terms of some physical thing, that what is it that it exactly is denoting. Okay, so yeah, go ahead and think how you can solve this. Anyone who would like to tell me what is he thinking? How do you feel this can be solved? Any approach regarding maybe element of choice? You can just type in what you're thinking. Just type in whatever you're thinking. I can comment on that. Length, okay. Okay, so guys, let us start. Let us look at the board. Everyone look at the board. See, let us say I'm creating a function that in its input somehow takes an input that is a string, okay. Somehow the input denotes a string. Everyone focus your attention here. This is really, really important, okay. Okay, now here I have to, let's say, decide the fate of first character, okay. Do I have choices here? Do I have choices, or I have to stick to one particular choice? What is your opinion about that? Can somebody tell me? Okay, so Akshay says I have got choices. What are the choices that I have? So guys, choices are available. Either I can consider this one a part of this two, or I can consider this one as a separate entity. Is it not? Is it not? Yes, so these are the two choices that I have. But hold on, had it been something like 4, had it been something like 4, then did I have a choice? Then I did not have a choice. Then I would have been forced to consider this 4 as D and then venture on to the remainder of the string. Is that not? How many of you are understanding that? To say yes if you are getting that, what I said. That my choices are dependent upon the character whose fate is to be decided. Now let's say I have got two choices here. Either I can consider it as independent, or I can consider it as not independent. So if this is independent, I'll mark it I, not independent N. So if this is independent, in that case, let me just remove it. I'm not going to correct it. If this is independent, that means this 1 is symbolizing what? That means this 1 is symbolizing what? Can you tell me that? Is symbolizing A. And if this is a part of this, then this 12 is symbolizing L. Now, if this was independent and I sacrifice this one for A, I venture into the remainder, which is 27101. And if I considered this 12 as L, then I venture into 7101. Is that clear? Is that clear? Let's say yes, if that is clear, the two choices that I have made. Okay, now the solution that I am going to get from here will be all possible decodings of this. So basically f of a string is a function that returns me a number, an integer x, which says there are x different ways to decode this string. So if there are, let's say, x different ways to decode this string and y different ways to decode this string, can I say that the answer for this will simply be x plus y? Can I say that? Can I say that? So Proma, your doubt is right. Even that corner case we would handle. Don't worry about that. Even zero corner case would be handled. But in context of this, can I say that number of possible decodings of this is x and possible decodings of this is y? The answer of this would be x plus y. Actually, yes. Why? Because all those decodings that I'll get from here would be something which is prepended with A and then have something. And all answers from here would be something which is prepended with L and then have something. So everything here, X different things, would be different from everything here, which is Y different things. So answer would be X plus Y. Is that clear? How many of you got that? Making elements of choice and then moving ahead to the remainder of my input. Yes, no, are you following what I just drew on the board? Then I can go ahead. Okay, now let's do one thing. Let's move ahead from here. Now I have to decide in this function call, I have to decide the fate of this. Do I have possibilities over here? Do I have possibilities over here? What are the possibilities I have here? I don't have a possibility over here. I just have one thing that I can consider this 2 as B. I cannot consider this as one thing because 27 is nothing. 26 is Z, 27 is nothing. Okay, so I can sacrifice this as B and then I venture on to 7101. When I venture on to 7101, again here, the only one choice that I have is to consider this 7 as G because 71 is nothing. And I move on to 101. When I am at 101, do I have choices? How many choices do I have when I am at 101? How many choices? 2 choices. Either I can consider this 1 as A and then I move on to here, or I can consider this 10 as what? J and then move on to here. Now guys, what will be the answer of this? So guys, you know, these are the tricky termination conditions which you will be clear if you understand the definition of this. The definition of f of something is how many decodings are possible of a given string. So can you tell me how many decodings are possible for a string that starts with 0? How many decodings are possible for a string that starts with 0? Think again. No decoding is possible because 0 is nothing. How many decodings are possible for 0, 1, 2? Forget about the actual input. How many decodings are possible? No decoding is possible. Are you getting that? Any string starting with 0, there are no decodings that are possible. So this is my termination condition. Whenever I end up at an input which maybe starts with 0, I simply have to return a 0 from there. Okay, cool. Now let's talk about this. When I am at f of 1, what happens when I am at 1? This 1 can be thought of as, I have only one choice here because I have reached the end of the string. I have reached the end of the string. So I can consider this 1 as A because there is no character next to it. And then I reach to end of the string. And here I can return 1. This return 1 signifies that if I have reached to end of string, that means I have taken a correct path all the way from root to leaf. That is one possible right decoding. To signify that, I am returning 1 from here. Is that clear? Yes, no, is that clear? So do you understand the 2 termination conditions? First, if the string is starting from 0, immediately return 0. If you have reached the end of string, which is null, return 1. Now you can easily see that this subproblem is exactly this, is it not? This subproblem is exactly that. So either you solve it again or you use a memorization data structure to solve it out. Okay. So clear about the termination condition, clear about the elements of choice. Now, few things that I want to understand over here is that there will be many corner cases because let's say had it been something like 2, then you would have taken two different branches. Either you could have considered this 2 as B or this 22 as I'm not sure what, whatever, and then venture into f of 101. So did you get the concept behind this? Did you get the concept like how problems are breaking down into smaller problems and how termination condition is being achieved and everything? Is that clear? How many of you are able to realize that? Say yes if you are able to understand. Okay, now one thing that I would want you to do is, I would not be writing the code here right now. Can you all take this as a homework? When you go back, try writing a recursion plus memorization based code for this. Can you all try that out on your own? Can you do that? That should be easy, okay? And if you get any doubt, just let me know. One thing, you don't need to pass a string. You can just pass the index. If you have the index, you know the character which is over there. And then you can either venture into, if you consider, let's say, this was 1, and then you have 2, and then blah, blah, blah. You can consider this 1 as A, and then you move on to the next character, which is first character. Or you consider this 12 as something, and venture on to the next character. And then you go on and on and on. There'll be a lot of if else based on what this character is and what the next character is, and whether that character is 0 or not, or whether you have reached the end of string. Can you think of that? How many of you already have those if else conditions in your head? If not exact, some if else conditions that you might have to write in the recursive code. Okay guys, so one thing that first write the recursive code, forget about the DP, first write the simple recursive code, and then you know the state. What is the state here? State is just the starting character, because f of 2 denotes the portion of string from second character till the end. So this problem just has one state, which is starting index of the substring that we are talking about. And if you memorize at the level of this, then you will be able to solve it like a DP problem. Cool? Got the hint? How many of you got the hints for that? How you can memorize it and how you can... Okay, great.